When we adding and subtracting complex numbers, we actually following the combining like term rule for adding and subtracting complex numbers. So when we're talking about adding, if I have two complex number, a plus bi and c plus di, c plus di, then when we try to adding them, we're going to adding the real number part together, a and c, and adding the complex number part, the imaginary part together, b and d, and then put the I on the outside. When we try to subtracting them, we do the same thing. We subtract the real numbers a and c, and then subtract the imaginary part b and d. However, here I do need to point out the operations, addition, for example, when we try to adding two complex numbers, the addition operation symbol to the final product is actually in between the b and c and the b and d. The addition sign between the a plus b and a plus c and b plus b is actually corresponding to the standard form a plus bi. So this one is not operation. It's just the form for the complex number. Same thing for the subtraction. When two complex number doing subtraction, then the subtraction operation is actually in between the a and c and b and d. When we try to multiply complex numbers, then we actually follow the FOIL method. So if I have a plus bi times c plus di, so I will follow it as ac. So I'm drawing the lines. Plus ADI plus BIC plus BIDI. Then we're going to combining them, putting the AC, putting the ADI and the BIC together. AD plus BCI. However, for the last part, I have II, which is I squared. And I squared is -1. So the last term will become 2 minus BD. Then I can also put in the AC and BD together. So in short, if I want to have a formula, then I will say if I want to multiply the A plus BI times C plus DI, it will equals to AC minus BD plus AD plus BCI. Similar things, we also have the special formula. If I have A plus BI times A minus BI is going to equals to A squared plus B squared. Here we're going to do a couple examples to using those formulas. So the first one is I want to add 3 minus 4i and -2 plus 6i. So this is addition problems. So that means I'm going to adding the real number part together, 3 and -2, and also adding the imaginary part together, -4 and 6. And I got 1 plus 2i. The second one I want to do is multiplication problems, that 5 plus 3i multiplied by 2 minus 7i. So I'm going to using the FOIL method, which is 5 times 2 plus 5 times negative 7i plus 3i times 2 and 3i times negative 7i. Combining them together, I got 10 minus 35i plus 6i minus 21i squared, where I squared is negative 1. So I adding 21. Now combining like terms, 10 and 21, I got 31. Negative 35 and 6, I got negative 29. So the answer is 31 minus 29i. To do one more multiplication problems, I want to multiply the 4 minus 5i squared. So I will do, to do one more multiplication problems, I will do 9 minus 8i times 9 plus 8i. So this one I can use in the FOIL method, or I can just using the formulas. So I'm going to do the long way using the FOIL method. So I'm going to do 9 times 9 and 9 times 8i. And negative ai times 9, I'm going to do negative ai times 9 and negative ai times 8i. So 81, 72i minus 72i minus a squared. So 64i squared. So you can see in the middle, plus 72i minus 72i will disappear. End up with 81 plus 64. Because I squared is negative 1. So we end up with 145. So if I do the formula versions, 9 minus 8i times 9 plus 8i. So I will do 9 squared minus 8i squared. 9 squared is 81 minus 8i squared, which is negative 64. So we still do 81 plus 64 and 145. Next example, I want to do division problems. For example, 5 minus 5i, so that's one complex number, divided by 3 plus I, a second complex number. Similar to rational expressions, we do not have division problems in the complex number too. All the division problem is actually bring it down to rationalize the denominator. So as I mentioned before, that we have a special formula, a plus bi times a minus bi will end up to a squared plus b squared. So here I want to talking about the relationship between those two complex numbers, a plus bi and a minus bi. We actually call them conjugate. And then the property, or the definition for conjugate is when they multiply, we just have the a squared minus b squared, or a squared plus b squared, because we have a complex number, so it's actually a plus b squared. So for this situations, 5 minus 5i over 3 plus I, we have to rationalize the denominator by multiplying the conjugate. Conjugate for 3 plus I is going to be 3 minus I. So we're going to multiply the conjugate on both numerator and the denominator. On the denominator, what becomes to 3 squared plus 1 squared. On the numerator is going to be FOIL, 15 minus 5i minus 15i plus 5i squared, where I squared is negative. So we end up with 10 minus 20i over 10. Simplify, we got 1 minus 2i. So as you can see, that the only additional process we did here is multiply the conjugate to rationalize the denominator. So no more i's on the denominator, and we didn't really do any traditional division problems. So similarly, if I have 15 divided by negative I, so I still have quote-unquote two complex number divide them together. Remember, complex number is more broader number system than the real number. So any real number is a complex number. So to do it, I still going to rationalize the denominator by multiply the conjugate of negative I. You can thinking about is I, you can thinking about is negative I. It doesn't really matter. So I'm just going to do I. So I'm going to multiply I on both numerator and denominator. So on the numerator I got 15i, on the denominator I got negative I squared. And I squared is negative 1. So negative of negative 1 will become to positive. So the answer is positive 15i. Okay, see here I want to bring up another concept, is the power of I. So I, by traditional definition, is square root of negative 1. So I'm now going to repeat my definition. But I squared is going to be negative 1. Now I cubed is going to be I squared times I. So it's going to be negative I, because I squared is negative 1. Then I to the fourth, you can thinking about is I cubed times I or I squared times I squared, which I squared is negative 1. So it's similar to negative 1 times negative 1, which is positive 1. And when you go to I fifth, it will repeat it as I fourth times I, which is 1 times I is I. And then I sixth, without doing any calculations, I know it's going to be negative 1. I7 is going to be negative I8 is going to be 1. I9 is going to be I again. I to the 10th power is going to be negative 1. I to the 11th power, negative I to the 12th power, 1, and repeat and repeat and repeat. So you can see that every time when the power of I reaching to a multiple of 4's power, it will always return back to 1. So that's the power of I. So you can thinking about example as, what is I to the 33's power? So we want to see how many 4's powers inside I to the 30, or how many 4's inside the 33. So if we're using 33 divided by 4, we got 8, have a remaining of 1. So we can see that there are 8 4's inside 33. So I can thinking about I to the 4th power to the 8th power. So 4 times 8 is 32. And remaining 1 more I. Okay, why I using I to the 4th? Because I to the 4th power equals to 1. 1 raised to any power is still going to be 1. So it's still going to be 1 times I. So we end up with I. So I to the 33 can simplify into I. So another example we can see is I to the negative 14. So we still want to see how many 4's inside negative 14. We know if we're using positive 14 divided by 4, we got 3. And then there are 2 remaining. However, because it's negative 14, if I just using the 3 and 2, what I will end up with is going to be I to the 4th power to the negative 3 to get negative 12 and multiply by I to the negative 2. It's doable, it's just creating another layer. I need to also changing I to the negative 2 to something else. So what I want to do is, instead of 3 and 4, I actually want to go a little bit higher by changing it to 4. So go a little bit higher than 3 because of the negative. And let me just erase this part for temporarily. And then I force to the negative 4 will become to I to the negative 16. And in order to get negative 14, I need to add a 2. Okay, and because of that adding the 2's, I'm able to write I to the 4th power to the negative 4 times I to the positive 2, I squared. Again, I to the 4th is 1, so still 1 times I squared, which is negative 1. The last example we want to do is we want to solve equation 2x squared minus 2x equals to negative 5. Since this is under the complex number section, so we know the answer is going to be a complex number. So to solve it, I'm going to rewrite it as 2x squared minus 2x plus 5 equal to 0 because I want to use in the quadratic formula where 2 is A, negative 2 is B, and 5 is C. So x is going to be negative b plus or minus square root of b squared minus 4ac over 2a. So negative b becomes to negative of negative 2. And then b will be negative 2 squared. ac is going to be 2 times 5, and a is going to be 2. So x will becomes to 2 plus or minus 4 minus 40 over 4, where 4 minus 40 is going to be negative 36. Negative, that means we're going to end up with I. And 36 is 6 squared, so 6i over 4. Simplify everything. We will end up with 2 over 4 plus or minus 6i over 4, which is 1/2 plus or minus 3 over 2i. And that is 2 answers. For this situation, you do not need to breaking down into 1/2 plus 3i over 2 and 1/2 minus 3i over 2 is the same thing. And then we cannot really continue from that point, so we just leave it like that.